Okay, so now the mic's working. Everyone can hear me okay? Okay. Well, a reminder to everyone who is watching, the chat for this is in Discord. Please get into the new chat channel, not the one from last week, but the one that is set up for. I'm sorry, not the one from Monday, but the one that's set up for today. So it should be on Discord. It should be the 2020-03-25-930 class above the place where everybody is in the chat. So you should be in that room up there. I can't show you the room without revealing everybody's name that's on. So I can't show you that. Anyway, here we are. A couple little technical things that have now been working. One, I discovered that the issue, I think I told you this, is that the tablet overheats when you're streaming to it. So what I'm going to do is I'm going to stream over the computer, and then when I need to write, I will switch to the tablet to try to keep down the length of time that I am writing. I have ordered a backup tablet. I have ordered a cooler. One of the people in Discreet suggested that I get a cooler for this, and as soon as they get here, I will have that. Okay, so there are any questions before we begin? Okay. I don't see any questions in chat, so I will keep going. There was a question about the notes. If you see that in chat, because Problem Set 10 asks you to scan your notes, stick those things in the scanner. Yes, class has begun. Let's see, class has begun. There you go. And as you can also see, I changed my profile photo because I hated that one. Okay, so since there are no other questions in chat, I will just go ahead and get started with the quiz. How was this quiz? How did we feel about this quiz overall? Oops, I lost my poll when I touched that. 5-poll quiz. So how do we feel about this quiz overall, 1 to 5? I got the little poll going here. Okay. Let's talk about it. The first thing, this was from before. These are details, don't care. As a matter of fact, we don't care so much that we are going to shrink these to emphasize the fact that we don't care about these details. This is the preamble details, stuff like that. Then this is the stuff that's important. If f is differentiable at x, and if f has a local min or a local max at x, then f prime of x equals 0, and that's the one we did before. Any questions about that? Yes, I see your question about the inflection point. I will get to that in a moment. Any questions about the first problem? Okay. So moving on, let's talk about the second problem. The second problem is a little bit more involved, and I didn't get as far as I wanted to last time because of all the technical issues. So let's go ahead and go over the whole problem. The first part, of course, I want to find an inflection point. What I want to find, because what I want to find is the mins and the maxes of f primes. We might as well just put that in there. I'm looking for the min and max of f prime, et cetera, et cetera. So what I need to do is I need to take the first derivative, and then I need to take the second derivative. 1 to 5, how do we feel about that. So, so taking both derivatives, how do we feel 1 to 5? And the fact that that's what we need to do. So I take the derivative of both of these things, and I set the second derivative equal to 0, because that's what I'm interested in. I'm interested in inflection points, which are mins and maxes for which are mins and maxes for the first derivative. So what I'm going to do is I'm going to set the second derivative. I'm going to set it equal to 0, and I have a suspect point. Remember, I don't know that it's there, but I suspect that there's an inflection point at 4. So I only have one of these. So what I do is I set up this nice little chart here. This is bad because this is actually confusing, that line. So what I do here is I set up this nice little chart. So I say, okay, at 4, my second derivative is 0. And the question is f double prime negative or positive? And if, because if f double prime is negative, that means it's concave down over that interval. And if f double prime is positive, that means it's concave up. So I pick a couple test points. I found the test point that was in here. That test point was 0, because I always like zeros. Zeros are easy to deal with. And when I plugged in 0 here, I get f double prime of 0 equals 0 over 2 minus 2, which is, of course, less than 0. That means that over this entire interval, because the intermediate value theorem tells me that if I don't cross 0, I can't change. So because the intermediate value theorem tells me that, I know for this entire interval, the second derivative must be negative, because this derivative is continuous, and if I don't cross a place where the derivative is 0, I can't change from if I don't cross a place where the derivative is 0, I can't change from negative to positive. So I have to go through 0 in order to change from below 0 to above 0. And because of that, just any point to the left of this, because there's no other values. If there were multiple values, I'd have to choose one in between on the interval. But just any point within negative 0, 4 is going to tell me whether the thing is positive or negative. So how do we feel about that 1 to 5? Okay. And I see in chat that everyone's talking about using the quotient rule. You can use the quotient rule, but it's much easier to view this thing right here as a 1/12. So if you view this thing in front as a 1/12 times x cubed, you just have a polynomial. If you use the quotient rule here, you're going to wind up with a piece that's here that's going to wind up canceling, which is fine. But it's a lot of work and you can make silly little mistakes. So again, just think of this as 1/12 times x cubed. But you could do the quotient rule if you so desire. Okay, so I do these two things and I find out that here it's negative and here it's positive. That means f is concave down over this portion and concave up over this portion. Okay? So what I get is that at x equals 4, because I can type, there he goes. There we go. I get that at x equals 4, that's embarrassing, that I have an inflection point. Are there any questions about that? And now this one's supposed to be in blue. right? So everyone tell the 11 o'clock class that I totally messed it up yesterday. Sorry, I messed up the rubric completely this morning when I was doing it. So I do have an inflection point at x equals 4. So technically, the inflection point is both the x value and the y value. Okay? So I can find both of those. I can find the y value by just subbing in 4 into my original equation. And I wind up with negative 30. Did I do this right this time? 4 squared, 16 times negative 2. Yeah. So I wind up with negative 32 over 2 as the y value, which is screwed up here because that's where the x value should be. This is just all kinds of horrible this morning. There we go. So technically the inflection point is the x value, negative 32 and over 2. But just the x value is fine. And note this is different than the absolute min or max, where we only want the y values, and this is because we hate you, and not you in general. I mean you in particular, Mrs. Smarty Pants in there that's showing all her paper. I'm just kidding. We love you. Any questions, comments, issues, suggestions, thoughts? Okay, so how do we feel about part 1, 1 to 5? And great. So my 1 to 5 went away again. So how do we feel about part 1? All right. Yeah, so I plugged 4 into the function, and that's how I got it. Okay. Well, the nice thing about doing this nice little chart here is that now when I say over what interval is f concave up, I say negative infinity 4, and then I say, well, go see my chart, you lazy bum. I don't need to do the work again. So I answer basically all 3 parts. I hate my life. There we go. So I solve all 3 parts at once. Of course, I just messed up everywhere because I said they were, but then I did them under the wrong part. This is what I get for waking up early in the morning. Any other questions? So everyone can, take a little clip of this and post it on YouTube and say, hey, watch a math professor totally screw up everything with a quiz. So there's a question about the test. I don't know what the test is going to look like yet because the test that we wrote at the beginning of the semester is now gone. It went out the window. It got coronavirus and died. So I have no idea what the test is going to look like. I have some idea because I wrote the original one. But of course, because we wrote all the test in advance before the beginning of the semester, this was inevitable. So we're going to change the test this weekend. I like usually when I write them, the question reads, what is the x value of the inflection points? What are the x values of any inflection points, to be specific? So technically, for the point, you need both values. I just like the x value, but I don't know what the question is going to end up reading after this weekend. Any other questions? All right, let's see how badly I can mangle the next one. Okay, I've already looked at some of your answers, and a lot of you thought you were looking at F because this was a little too subtle, where it said, the graph of the derivative right there, that this was F prime. Here, the title, I told you I was looking at the graph of the derivative, and a lot of people thought they were looking at F. So how do we feel about the fact that what I'm actually looking at is the derivative and not f, which is what I want to answer questions for. So how do we feel about that? What I'm actually looking at is the derivative, not at f. I'm looking at the derivative, and there were very subtle clues to tell you that. This is f prime, not f. This is f prime. So if I remember that if f prime is positive, then f is increasing, and if f prime is negative, that means f is decreasing. And if f prime, same thing. Remember this relationship between f prime and f double prime. F double prime is the derivative of f prime. And I also should remember so if I want to talk about when f is concave up, what's happening is that f prime is increasing. Right? And f double prime is positive. So if you remember this little chart, it will help you a lot. You can also add to this chart various things like the min, max, and things like that. Any questions about that? Okay. So over what intervals is f increasing? Well, f is increasing wherever f prime is above the x-axis. So f is increasing from -2 to 0, and then again from 3 to 4. How do we feel about that? 1 to 5. Okay. So we're a little shaky on that, but that's okay. We can fix it as long as we fix it now and not before the test. People are typing questions. That's fine. Could you have said negative infinity? Note the domain here. It's -2 to 4. If you say negative infinity, technically you're wrong. It's not defined farther than that, right? I've only got really -2 to 4 to talk about. Now, it's like half a point. Technically, it's incorrect, but you have the idea. Fussiness also went out the window with coronavirus. But it's like half a point. It's not a major deal, but it is technically incorrect. You technically need to say -2. Okay. Same thing. Over what intervals is f decreasing? Well, 0 to 3. Why? Because that's where f prime is less than 0. So the function, there's a question about this. The question is, it is increasing when it is over the x-axis. It's increasing when you have positive slope, but remember you're looking at f prime, not at f, okay? F is increasing when f prime has a positive value, right? Because if f prime has a positive value, that means f has a positive slope. Okay, so let me just show you something here. So these two functions, and I put them on different graphs because I want you to see this. This function right here is the red one up here is f. And this one right here is f prime. Okay? So your question, you see here how f prime is decreasing. But what I care about here is if I'm asking when f is increasing, it's not that f prime, it's that f prime is positive. Notice here that f is increasing all the way to 2. That means that f prime is going to be positive all the way to 2. Likewise here, f prime is positive starting at x equals 4 and going up. That means that at this point here, that means that f, so f prime is positive, that means f is increasing. So how do you feel about that, 1 to 5? Okay. All right. And again here, I want to know, so let's look at this again. So these two questions are closely related. Okay. And then let's look at the last one. The last two are the exact same thing, 2 to 4, because that's where f prime is increasing. Now, I'm asking where f is concave up. In other words, I want to know where the slopes are increasing as I move from left to right. Now, as I move from left to right in f, I want to know where the slopes are increasing. Well, that means the slopes are f prime, and that means that the slopes are increasing. That means f prime is increasing. That means that f would be concave up. So here, f is concave up, where f prime is increasing. That's from 2 to 4. And f is decreasing. And there's this question about d that I'll get to in just a moment. And f prime is decreasing wherever f is concave down, or vice versa. Wherever f is concave down, f prime will be decreasing. So here, f prime is decreasing from -2 to 3. Okay. I'm sorry, -2 to 2. I wrote it down correctly, but I didn't say it right. Now, there's this question about would you include 0? And the answer is yes. Remember, there's this technical definition about whether or not something is decreasing. And it's decreasing if the next number over is less than or equal to, right? So a flat line, this line f of x equals 0, is technically increasing and decreasing everywhere, okay? It's not strictly increasing, that's different, but it is increasing. And actually, this bit here is strictly decreasing because just to the right of that number, just to the right here of 0, just to the right of 0, I'm less than 0. And just to the left of 0, I'm greater than 0. So I am actually strictly decreasing the whole way, even though the derivative is 0, even though I have a stationary point. Okay, so does that answer your question? It's a small technical detail, but it is a small technical detail. So would it be okay if you wrote -2 to 0 and 0 to 2? Technically, it's incorrect. Technically, it's -2 to 2. Okay? And if you look at x to the 4th, you'll actually see that. So if I come back over here to Desmos, look at x to the 4th around 0. You see, that really, at 0, 0 actually is the minimum, right? Even though the second derivative is 0, you've actually still got, if you asked where was it a minimum, that would be it. And if you asked where it was concave up, well, it's concave up everywhere. So technically, it's incorrect. It is concave up over this interval and concave up over this interval, but it's more than that. It's actually concave up over the whole thing. Does that answer your question? A small technical thing. I'm more interested in this idea. I'm much more interested in this connection between these things. Okay, not in that small technical thing. I'm much more interested in this connection up here. Okay, so 1 to 5. How do we feel about that big thing? What f prime tells us about f? Okay. Just so you know, although, you know, there's also a question about test reviews. Yes, I will be doing test reviews, which brings me to another thing. I'm basically sticking to the exact same schedule. The test review will probably not be on Twitch. It'll probably be in Discord itself because we got up to 50 users. If more than 50 people show up, we'll figure something out. But I'm still going to also have the Wednesday night thing. So the Wednesday evening today at 5, I'm still having a problem session. If you wish to attend, name one thing you found memorable of the class. Nothing working. So, are there any questions for me before we put this to bed? Yes, you can use tangent lines to make sense of anything. You can actually even use secant lines to make sense of everything. But yes, you can make tangent lines to make sense of everything. Because that's really what happens. When I draw a tangent line and it has a positive or negative slope, it tells me whether or not the function is increasing or decreasing. And then I think about the slopes of the tangent lines to think about the change in the change. Okay. All right, so that's it for the quiz. If you have any questions, I will be hanging out later. Let's talk about what we want to talk about today. So, let's make this go away. Let's zoom in some more. There we go. So, today we're going to do something. I'm not the only professor that does this, but I'm one of the few. This is one of those topics that the book assumes you know beforehand. And that's proofs by contradiction. And there's a big section in the pre-calc book which no one ever gets to in pre-calc on proofs by contradiction. And so the book kind of assumes you already know it. And for some reason, if you get the big book, right, this is the essential calculus. If you get the big book actually has a section on this. But the art book just kind of assumes that you know it. And then it does proofs by contradiction in the section without explanation. So I'm going to actually spend a class talking about proofs by contradiction because I think they're important, but they aren't horribly important just for calc, but they get more important as you go on in mathematics. So I'm doing something again that, like, I don't know, 30% of you are going to absolutely hate. 20% of you going to get, it's going to be your favorite part in the entire class. It's going to be like, cool, that was so neat. And then, the rest of you will be like, meh. So I'm going to do it. I'm sure that other instructors are going to do it. Robert is going to do it. I'm sure other instructors are not going to do it. There will exist instructors that don't go over it. There will a lot of instructors will kind of mention it in passing. But I think it's an important thing in math in general. So let's take a little break from our, boom, boom, boom on calculus, and let's talk a little bit about proofs by contradiction. So last time we talked about the change in the change of the concavity in the second derivative. So how does everyone feel about what we're about to do? So 1 to 5, what we are about to do. And of course, someone's going to ask me, is this going to be on the test? You remember how on the last test there were these problems that, I didn't really need linearization. I didn't need to know it for the last test because I could get out of it by doing something else. That something else being a proof of a trig function. So do you need it for the last test? Is it going to be on the test? More than likely. Do you absolutely have to have it to survive? Probably not. I'm trying to get rid of these sunbeams that are on my shirt, and there's nothing to be done about it because the sun just comes right in the window at 9:30. So there's just do you have to have it? There are proofs on the test, or at least there were. Whether or not they're still on the test after, this weekend is another question. There are proofs on the test that are very clean to do with, that you can do the other way, but they're very clean if you do them with contradiction. Is it going to be on the test? Yes. Do you have to have it to get an A? No. But it does save you some time, and it's really, really cool. So again, we're going to do it in class today. At least I'm going to do it. Now, whether or not other people do it is, of course, another question. Anyway, so enough of that. Let's talk about it. What we want to do is we want to talk about proofs by contradiction, and we're going to do what is probably the most famous example of one of these, the proof that the square root of 2 is irrational. And then we're going to talk about Rolle's theorem, and we're going to prove it using contradiction. There's another proof. There's a proof by cases in the book, which you can also do, but the contradiction proof is just really slick and kind of fun. So we're going to do that one. And then we'll start the mean value theorem. If there's time, we'll do the proof. If not, that's fine. And then on Friday, you're going to be in peer leading, and in peer leading, you're going to do all the intuition about the mean value theorem. Mean value theorem is very nice, and you can use it to do a lot. For instance, if you want to prove the full version of L'Hopital's rule, we get kind of the diet version as the ratio of linearizations. But if you want the full proof, you need mean value theorem. We're also going to use mean value theorem to prove things that we need for module 4. So it's one of those big cranks that lets us do a lot. Okay, any questions, comments, issues, suggestions, or thoughts? Okay. Well, this whole thing, and yes, I'm sitting in front of the triangle. Get over it. This whole thing, the big idea is that a statement cannot be both true and false. Okay, that's a contradiction. If we have a statement that leads to a contradiction, that statement must be false. So in practice, what we're doing is we're assuming the opposite of what we want to prove. And then we show that our assumption, okay, the thing we wanted to prove was false, or true in this case, led to a contradiction. So to prove that P is true, we assume that P is false, and then shows that that leads to two statements, Q and not Q, that have to both be true, right, at the same time, if P is true. But of course, we can't have something both true and false at the same time. Therefore, not P must be false, which implies that P is true. Let me do an example. The example, and the famous example, is going to kind of clear it up for you a little bit, what we're doing here. So let's do the most famous example of this, and this is Euclid's proof that the square root of 2 is irrational. So let me go to the pen display. It works. Okay. So, do we remember what a rational number is? I put some examples. Give me some more examples of rational numbers in chat. So, my examples were 1 over 2, right? So, if you have a positive number, then you have that positive number x is rational if there exists two positive integers, so that x equals p over q. Go ahead and give me a few examples of rational numbers in chat. Yep, 7's a good one. It's 7 over 1. Other examples, 1.333333 repeating, or 0.33333 repeating is, what's 0.3 repeating? Right, 0.3 repeating is 1/3. Other examples, 3/6, is the number 1/2, same thing. So how do we feel about the definition of what it means for a number to be rational? All right. Um, I'm not sure if I'm losing voters or if I'm losing viewers. Which do you think it is? Anyway, I'll watch the Twitch log and see. Or people are downstairs, grabbing soda, which is, also a valid thing to do when you're teaching remote. Anyway, so there were these people called the Pythagoreans that went around saying, well, every number is rational. And they talked about music, which was nice, being the ratios, these, harmonics. They talked about harmonic means. And they went around screaming that every number is rational. And Euclid came along and said, no. And it was actually people before Euclid saying this. One of them got killed for saying it. But there do exist numbers that are not rational. And this particular proof of this fact goes back to Euclid. And that is the fact that the square root of 2 is irrational. Now, the first thing is that the square root of 2 must exist, right? If I have the Pythagorean theorem, I have a triangle of length 1 and another triangle of side of length 1, and that means that, 1 squared plus 1 squared has to equal whatever c squared is, which means that's the square root of 2. It must be that length. So we know that the square root of 2 exists, assuming that the number 1 exists, and that we have things called triangles. So the question is this a rational number? I want to prove that it's not. Now, to prove that it's not, I'm going to go, suppose otherwise. And you have to do it when you do it when you do this proof. You have to go. When you say suppose otherwise, it's not enough just to say suppose otherwise. You got to go, suppose otherwise. Okay, so let's suppose otherwise. Now, what does suppose otherwise mean in this context? In other words, suppose that the square root of 2 is rational. Right? I want to prove that it's irrational, so suppose the exact opposite. Suppose otherwise. Suppose that it was rational. Well, if it's rational, that means there's a fraction. It's got a fractional form. And because it's positive, that means that I've got a ratio of 2 positive integers. It's rational. What's more, every rational number has a reduced fraction form. Right? 3/6 is the exact same thing as 1/2. How do we feel about that? Every rational number, from things, every rational number has a reduced fraction form, 1 to 5. Right. Okay. So there must exist positive integers, p and q, so that the square root of 2 equals p over q, and p over q is the reduced form. Okay. So positive integers. I didn't write the word integers. Let's move Euclid a little bit. Euclid's not moving. Oh, well. So there exist these two positive integers, p and q, so that p over q is the reduced fractional form. There you go. Of the square root of 2. Okay. Well, that means I multiply q over to both sides, and I get that q times the square root of 2 equals p. Implying that q squared times 2 equals p squared. That means p squared must be even. Right? I've got a number. I've got an integer. Q squared is an integer. I multiplied it by 2. That means whatever comes out, I don't know what it is, but I know that it has to be even. 1 to 5, how do we feel about that? Okay. So we're a little shaky on that. P squared must be even. What 8? Oh, okay. So my Q's look confusing. And I just now have failure. So let's do this here. So let's do this. Let's switch back to the other one so I can make this clear. So the question is, how are we just supposing otherwise? We don't know that square root of 2 is irrational. Okay? We want to prove that it's irrational. Now, in order to prove it's irrational, what we're going to do is we're going to assume the opposite. We're going to assume otherwise, and then we're going to find a contradiction. So what I'm doing over here, mouse disappeared on me. Okay, so this right here, this actually says that's a Q right there. We only need one dot. That's times the square root of 2. So I took Q and I moved it over here. And that implies that Q squared here, that's a Q. That implies that Q squared times 2 equals P squared. So P squared equals 2 times some number. How do we feel about that? I'm missing my TA. I was supposed to have a TA and I don't. So how do we feel about that? That P squared must be even because it's 2 times some number. Okay. All right. So what I'm going to do here, and as I said, I ordered a back. So my tablet just overheated again and went and did its death thing. I have ordered a new tablet. It's supposed to be here on Friday. So I will have 2 tablets and I will be able to go between the 2. And I ordered a cooling pad for this tablet so that I can cool it quickly. but the tablet has died from overheating and had to be rebooted. So it's coming back up shortly. So p squared must be even. Now, if p was odd, if I take an odd number and I multiply it by another odd number, what do I get? An odd or an even number? Now, if I take it, not add, I multiply. Right. So if I multiply two odd numbers together, I wind up with an odd number. So if p was odd, p squared would be odd. So p must be even. Now, if p is even, what does that mean? What does it mean for a number to be even? Since p is even, p over 2 is some integer. Call it n. Right? Since p is even, p over 2 is some integer. Let's call it n. Yeah, it's divisible by 2. And it's a positive integer as well. So, therefore, what's true? Well, therefore, p equals n times 2. How do we feel about that? 1 to 5. Okay. So p is even. That means that there's some positive integer, n, so that p equals n times 2. Okay. So, that means that q squared times 2 equals n times 2 squared. And that implies that q squared times 2 equals n squared times 2 times 2, which means that q squared equals n squared times 2. And that means q squared is even. By previous argument, q must therefore be even. Right, n equals p over 2, so p equals n times 2. So I plug it into that equation for p, I plug it in there. I could have, but I kind of did, right? I get n squared. That's what I did right here. I got n squared times 2, right? N squared times 2 squared. Q and you mean P and Q, right? P and Q can't both be even. But what's the thing what's my problem? What did I say was true about P over Q? Ah, yes. Yes, there it is. If P and Q are both even, then P over Q is not the reduced form. No, the how do we feel about that? 1 to 5. Oops, no, I meant to say not that. Wait, make it go away. Don't vote on that poll. There we go. Why can't P and Q be even? Because I said P over Q was the reduced form. Okay? So if I have 2 over 4, is that the reduced form? Right? No, because I could divide both sides by 2 and I get 1 over 2. Does that make sense? Okay. Um, the point is that if I can, okay, so the question is, what if we have 3 over 6? It becomes 1 over 2, but that was not even in the first place. Yes. But another example of a reduced form of a non-reduced form fraction is 2 over 4 or 4 over 8. So the point is that if I wind up with a fraction where both of the numbers are even, okay, if I wind up with a fraction where both of the numbers are even, I can divide both of the numbers by 2. Okay. So it's not that that's the only form of a non-reduced fraction. 3 over 6 is a perfectly good example. And if what I wanted to prove was that the square root of 3 was irrational, I'd wind up with two numbers that are both divisible by 3. And that's what you're saying with 3/6. But the point is that it can't be reduced. And the reason it can't be reduced is that I can divide both the top and the bottom by 2. It's a little weird the first time you see it. It's really cool, but it's weird. Now, let's look at the immediate application of that. And the immediate application of that is Rolle's theorem, this idea. It doesn't work if both numbers are odd. Think about 5/7. 5/7 is not, those are both prime numbers. 5/7 is reduced form. So the question was, does it work if both numbers are odd? And the answer is no. It only works if both numbers are divisible by another number. So a number is odd if it's not divisible by 2, which is something different than saying that a number is even. A number is even if it's divisible by 2. The real thing in here is the divisibility, not the evenness, but the fact that both of the numbers are divisible by 2. Therefore, I can create a more reduced form. Okay, so let's look at Rolle's theorem. Now, Rolle's theorem is this result. Let's put him up there. Well, Rolle should be up there. Rolle's a cool guy. Let's put Rolle's up there. Here he is. Nope, he's not there. So Rolle's theorem says the following. I've got a bunch of stuff that's preamble, blah, 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 blah. Who cares? And Rolle's theorem says the following. If I have a function that is continuous on a closed interval AB, differentiable on the open interval AB, and if the two endpoints are equal, then there's some point in the middle where the derivative is 0. Okay. And this is in your book. Yes, the notes are going to be posted with the writing on them. What we're showing, the question is, so basically we're looking for a P over Q that is completely reduced. No, we're showing that there wasn't a P over Q that was completely reduced. Because there can't be, because if there was, I could always reduce it by 2, both the top and the bottom. So in other words, I could infinitely reduce that fraction, which is absurd, right? At some point, I have to stop. The Euclidean algorithm says at some point I stop. I can't keep dividing numbers by 2 forever. I can't divide a finite number by 2 forever. Does that answer your question? Okay, so let's move on to Rolle's theorem here. Rolle's theorem is kind of cool. Rolle's theorem says that basically if I have the endpoints being the same and the function's differentiable on the inside and continuous on the outside, then that means there's some point in the inside where the derivative is 0. So if I have, that was a horrible axis. If I have something that looks like this, okay, let me put on the silly gloves so that the machine stops like yanking me around, which annoys me. So I have a function here, and let's call this number A and this number B. And f of A equals f of B. And the function goes something like this. It's continuous and differentiable. That means there's some place in the middle, u. There's some x value in the middle, so that f prime of u equals 0. That's what Rolle's theorem is saying. So how do we feel about the statement 1 to 5? Yeah, it's all... Okay. Let's prove it. And the proof is slick. I love this proof. Nope, we want purple. Suppose otherwise. Suppose otherwise. Suppose there was no U. Okay? Where are the mins and maxes? By the extreme value theorem. So, if there were none, then by the extreme value theorem, excuse me, I'm going to go stuff my computer in the fridge. I'm actually not going to do that. What I'm going to do is turn it off, and then hopefully it will cool down before the next class. Okay, so by the extreme value theorem, since this function is continuous on a closed interval, f must have both a min and a max. Okay, how do we feel about that 1 to 5? Yes, it could have more than one, but I just care about the fact that it's got to have one. I mean, it can't have more than one min, because a min is a y value, right? It could have multiple local mins, and it can have more than one place where the derivative winds up being 0. But let's just suppose otherwise. Suppose there is no such u. So how do we feel about that statement? Okay. So if the min is in the middle, since if the min occurs in the middle, since f is differentiable, then by Fermat's stationary point theorem, the derivative there is 0. So the minimum must be at an endpoint. Is everyone on board with that? If the min occurred in the middle, then by Fermat's stationary point theorem, the derivative there must be 0. So the minimum must be at one of the endpoints. It can't be in the middle. Now, the same thing applies to the max, right? How do we feel about those two statements, 1 to 5? I did it again. How do we feel about that, 1 to 5? Okay. Are people just no longer paying attention? Since everything just went to absolute kapooey? Okay. We got some 4s, we got some 5s. We got a lot less responses now than we did at the beginning. Okay. The middle, because then f prime would also be, f prime would be at the max. So the maximum must be in an endpoint. Okay? But the endpoints are equal. Now let's call what should we call this number? Let's call it T. And call the min S. All right, is everyone on board with this? These are y values. I've got one that's big and one that's small. But the endpoints are equal to each other. So the outputs, these y values, this output, right? I've got every number for every x, f of x, in other words, in other words, for every x, f of x is less than or equal to f of a. A less than or equal to sign. That's what's after that. There we go. That's the command, but I forgot I wasn't in math mode. Right? So f of a is both the min and the max. And f of a equals f of b. That means that every x in the middle, okay, is equal to f of a. Okay? Right? So let's get rid of this thing. Let's get rid of this statement. That's bad. Who cares? Who cares what we call them? But the endpoints equal each other. F of A equals F of B. In other words, we'll just call this equals max and min. That'll be easier. How do we feel about that? 1 to 5. Yeah, it's about a 3 for most of you. Zen about it. It's kind of cool. It says, and I can't draw because my drawing computer is now. But what it said, I dropped it. Now it's going to be really broad. What it says is that if I try to make it so that that weren't the case, then I actually made the thing worse because I made a constant function whose derivative is 0 everywhere. Okay? It's kind of a tricky thing. Just think about it. I got 2 more minutes, so hang with me just 1 more second. Let me state the intermediate value theorem. Okay? So what I'm going to do to state the intermediate value theorem is I'm going to take Rolle's theorem. I'm going to copy it, and I'm going to paste. But instead, I'm going to say Cauchy I'm going to say the intermediate value theorem. And the only thing I'm going to change in the whole thing is I'm going to get rid of this condition here. And what I'm going to say instead of that is that f prime of u equals f of a minus f of b over a minus b. Shoot. Why does my prime up there now? I don't want him up there. Anyone know how to make my prime come back here? Great. So that's the only change I'm going to make. And of course, I need to stick Cauchy's picture there too now, right? Yeah. There we go. All right. Are there any questions? I'm sorry, I've run. I'm right on time. Any questions, comments, issues, suggestions, or thoughts? Median value theorem, yes, thank you. Yes, so the mean value theorem, not the intermediate value theorem. I am sorry. My brain is on the fact, I'm using slots, short-term memory slots, because my brain is on the fact that this computer is still on the fritz. Any other questions about that? Okay. 1 to 5, how do we feel about this statement? Oop, dadgummit, now it wants to paste Cauchy. Someone make me some emotes with like pictures of Cauchy in them instead, right? That's what I need to do with my time. I need to have an emote of Euclid and of Archimedes and of Cauchy and of all these people. Okay, so proof may be forthcoming on a video. We may skip the proof, but it's a cool proof. You basically just use, it's in the book, you use Rolle's theorem and you just kind of, you define a new function and you apply Rolle's theorem to it. You can reduce, what it does is it reduces Rolle's theorem to just a special case of the mean value theorem. All right, are there any more questions, comments, issues, suggestions, thoughts, complaints, hatred? I'm noticing that the totals on my polls from the beginning of class are much greater than my totals for polls at the end of class. So I suspect that people have gone, no more, and that I've lost their attention. But anyway, that's okay. It is online learning, and we are trying our best. Any questions? Okay, so the quiz, remember there are two peer leading quizzes, pre-assignments, one peer leading quiz, two peer leading pre-assignments online for Friday. The first one is the normal pre-assignment, and the second one is to make sure that you're on Discord and all set to go for Friday. Also, there are web assigns posted for today and tomorrow. Weekend Sunday web assign to come. All right. Any other questions? You're very welcome for all the hard work. I'm glad you guys have a good time. Something tells me I'm not going to see a bunch of you next. Some people like last time came to the 11 o'clock. Something tells me that's not going to happen. I really might. Some of you might have brain hurt. Okay, so yeah, so people are asking how it's going to work on Friday for peer leading. What you're going to do is you're going to come in and you're going to you'll see it on the quiz. But what's going to happen is you're going to choose a group to get into. There'll be all these group channels for chat. And then when you jump into the group, what you're going to do is you're going to do peer leading as normal. Bring your phone because you'll do the quiz online just as normal, but also, so you'll do it on your regular computer, but also have your phone. Have your phone up on Discord and your computer up on Discord so you could take pictures of your work, like someone whose name I won't mention because I don't want to violate her privacy on a public forum was doing today while we were going over the quiz, and she was correcting all my answers. Do that, because then you can take pictures of your work and share them with your groups in chat, and it helps you collaborate. Okay, any other questions? Okay, then I will see you guys Friday or the next Monday. Or tonight. Remember, tonight, 5 p.m. Problem session. Okay.